Hello everyone, in this video we're going to look at a tank emptying problem where you have a tank that's filled up to a height h with some liquid and it has a leak at the bottom, and this leak has some velocity v sub h that we don't know just yet, but we're going to try to figure that out using what's called Torricelli's law. And the goal of this problem is to first find v as a function of h using Torricelli's law, and second we're going to use a volume balance to try to figure out what is the time it takes for this tank to completely empty. This volume balance is going to be a differential equation because what we'll find is that our velocity is not a constant. It'll depend on time, it'll depend on the height of this liquid, which might make sense because as there's higher liquid, there's going to be more hydrostatic pressure, which will force this liquid out faster. Our first step, as I said, is going to be to find velocity as a function of the height. And we're going to use what's called Torricelli's law. We're actually going to derive Torricelli's law or Torricelli's theorem. And the way we can do that is using the conservation of energy. So this is also known as Bernoulli's principle. If we have a steady flow, the energy at two different points is going to be the same. So let's start with one point at the top of this tank. This point here we'll call point 1, and a second point right at the outlet here. We're going to call that point 2. What we can do is outline the different kinds of energy in this problem. So we have the pressure, P1, plus 1/2 rho V1 squared. This is the kinetic energy at this point, plus the potential energy, which is going to be rho G H1, the height of point 1. And this is going to be equal to those same quantities evaluated at point 2. So that's P2 plus 1/2 rho V2 squared plus rho G H2. Now, first thing we can do is figure out how does this simplify a little bit. So since both of these 2 points are exposed to atmospheric pressure, we're saying that this tank is open to the atmosphere. So we have P atmosphere up here. There's also P atmosphere right at the outlet because this leak is exposed to the atmosphere. So that tells us that P1 equals P2, and these are both equal to our atmospheric pressure. And because of that, we can cancel these 2 terms out. So there's a few terms that we can get rid of right away. The second term that we can simplify here is this term right over here. The height h1 is just going to be equal to our h as a function of t. So we can say that h1 is equal to h as a function of t. And then this term over here, let's say that our leak here is at essentially right at the bottom of the tank. So then we can say that h2 is equal to 0. So that'll get rid of this term as well. So what we're left with at this point is 1/2 rho v1 squared plus rho gh is equal to 1/2 rho v2 squared. Now the simplification that Torricelli made, which will make this problem look nice and it'll give us a nice equation for v as a function of h, is that this container is sufficiently large, that this container here is much bigger than this hole coming out here. And so that, let's say that our area, our cross-sectional area is given by big A. Our cross-sectional area for this here is going to be a lot smaller, so we'll call it little a. We're basically assuming that our big A is much larger than our small a. And if we make this assumption, we can say that the velocity at point 1 is close to 0. So v1 is about equal to 0. And this might make intuitive sense if you have a small leak over here. There's not much change in the volume of liquid as a function of time relative to the total volume at the starting point. Obviously there's some change because we're doing a tank emptying problem. It must empty eventually, but the velocity here at the top is still much smaller than the velocity coming out of the bottom, and it won't impact our whole energy expression. So if we assume v1 is about equal to 0, this term will go away, and we're left with rho gh is equal to 1/2 rho v2 squared. And we can solve here for the velocity. These density terms go away. We get v2 is equal to square root of 2gh. So here's our expression for the velocity. We finished that first part of the problem we set out to do. So here, find v of h. That's complete. Now we need to think about what this volume balance looks like. For this step, we're going to use a volume balance to find the time to empty a tank. And what a volume balance means is we're going to say the change in volume in V, this is a capital V for volume, is going to be equal to what comes in minus what comes out. So if we write this in differential equation terms, we get dV dt is equal to, again, in minus out. There's nothing coming in, so that's a 0, minus what's coming out. So what's the volume per time coming out? That's going to be equal to our volumetric flow rate out, which is our velocity, again, as a function of h. That's this term right here, times the cross-sectional area. So that's our A. These units work out. Velocity has units of, let's say, length per time. A has length of length squared. So this works out to be units of volume per time, which will match our differential equation over here. So this is the basis of our volume balance. Now we said earlier that our velocity is a function of h, and we said that that was equal to the square root of 2gh. So what we'd like to do is rewrite this expression right here in terms of h. So let's say that we have a cross-sectional area up here of capital A and a cross-sectional area over here of little a. That's what we decided earlier. We can rewrite our volume, capital V, is equal to the cross-sectional area times our height as a function of time. So from this, we can also say that the derivative of velocity with a function of t, since our cross-sectional area is a constant, would just be equal to a times dh dt. So if we plug these two expressions in, we plug this in for our volume, and we plug this expression here for our velocity, we can end up with an expression that we can solve. So that'll give us a times dh dt is equal to negative a cross-sectional area times 2gh. And this is going to be our differential equation that we can use to solve for h as a function of t. If we solve that out for when h is equal to 0, that'll give us the time it takes to empty the tank. So all that's left to do is solve this differential equation for h. This is a separable differential equation because we have h is the only function of t in this expression. All of the other terms are constants. So we can bring all the terms that don't involve h, so that's this a and that's this dt, to one side of the equation, and we can bring the square root of h to the other side of the equation. We'll end up with dh divided by square root of h is equal to negative little a over big A square root of 2g dt. And we can integrate this expression. So let's integrate this. We're going to integrate from h is equal to capital H to 0. If you remember from our diagram, our height at time equals 0 is this value capital H. So that's what this term here is. And we're integrating the right-hand side of this equation from 0 to t. When we do the integral, this is h to the minus 1/2. So that'll turn into h to the 1/2 times 2, which again, we're evaluating from capital H to 0. And this one just integrates to the same expression here of all these constants times t. And so if we evaluate this, we get twice 0 to the 1/2 minus capital H to the 1/2. So we just get a negative h to the 1/2 on the left-hand side of this equation is again equal to this expression right over here, t. And what we want to do now is solve for t, because this value of t corresponds to the time when our tank is completely empty. So if we start solving that up here, we end up with, I missed a negative sign here, but on the left-hand side we have negative 2h to the 1/2. On the right-hand side we have a negative little a over big A, 2g t. Solve that for t. We can cancel out the negative signs. Here's one way of looking at that expression for t. We can simplify this a little bit by combining these two values. 2 divided by the square root of 2 will give us the square root of 2 on the numerator. So that'll give us square root of 2h over g. We can put this all underneath the same square root symbol times this ratio of cross-sectional areas, big A over little a, is equal to t. So here's our expression for the time it takes to empty that tank. We can try to think if this result makes intuitive sense. So first off, if you keep the cross-sectional area constant while increasing the height, as you might expect, that's going to increase the amount of time it takes to empty the tank. And similarly, if you hold the tank's height constant, but you increase the cross-sectional area, that will again increase the amount of time it takes for the tank to empty. If you increase the size of this outlet's cross-sectional area, that'll probably increase the volumetric flow rate leaving the tank, which will accelerate the time it takes to empty the tank. We can also do a little substitution here. Let's say the volume is equal to our cross-sectional area times the height of the tank, and we can plug that in here. And then in this case, we end up with T is equal to our volume divided by the cross-sectional area of the outlet, and we need to move that value of h to the denominator, so now we get root 2 over h times g. In this case, what we can learn is that if we keep the volume constant while increasing the height of the tank, that'll basically make this tank a lot taller and skinnier rather than larger and wider. If we make the tank taller and skinnier, that will decrease the amount of time it takes for the tank to empty because this height is on the denominator now.